design a trajectory now that tries to get back. It doesn't have to get back all the way to the goal, it just has to get back to one of the other trajectories I've already solved in the system. So it's a tree that's being formed. Okay? And then I'm going to compute the stabilizer for that and compute its funnel. And if I do that a few times, and the claim is with just a handful of trajectories, I'm going to fill the space with these funnels. And actually the claims of filling the space are fairly strong. It gives probabilistic feedback coverage is what we're calling it. So there's a set of initial conditions which is in the reachable, the controllable space where there is some solution that will take you from that initial condition to the goal. And we can claim that we will, as time goes to infinity, that's the weakness, as time goes to infinity, we will get every initial condition that can get to the goal, will get to the goal with this controller. Okay, so because any finite measure region in a controllable set that's not in somebody's funnel will eventually be sampled, even at random, and then eventually retrieved by trajectory optimization. So we can construct artificial examples where we know that the system can't cross this red line, it's supposed to get to this goal, and the algorithm will just start populating this, approximating this red line with ellipsoids in that case. That was the representation we used that day, that will eventually fill that space.
So what if the linearity is not controllable?
Right. So this is always assuming controllability for that statement. But there's there's obvious things you can try to do there. But the default statement is for controllable systems. Yeah. Although of course the trajectories don't need to be controllable. The fixed point needs to be controllable. Okay. So this works for a lot of the systems that I care about in life. Under actuated systems. If you'll introduce me to saying I worked a bit on that. Cart pulls, acrobats, these walking robots, right? So this is just a simple example on a cart pull. Whenever the light turns on, then he's running the controller. Okay, and it's not. This is lots of controllers that will stabilize this. It's a little harder with the with the constraints on the cart, but it's not a hard problem. It's just nice to see that the algorithm really works on the real system. And it works not just getting to the top, but it actually, with the proper models of the cart pull, it never leaves a funnel that it started in. And this is how we did perching. Okay, so for the perching plane, we spent a long time building the model of the post-stall dynamics. Once we had that model, all we had to do, well, it took a long time, but what we had to do was just take some nominal condition we care about, design a trajectory that gets you to the perch, close that, stabilize that trajectory with even linear feedback, and then if we find a new point, that initial condition we care about that's not in our funnel so far, we just add it back to the nominal tree now and add it to the plan, and we just